Okay, for this example number 5, I'm choosing the 2 kilogram, 3 kilogram, and Earth as my system. So both objects are going to be in my system. The floor is going to be external. My initial state I labeled in red. My final state I'm going to draw in yellow. So we know here that this will begin to fall down 1.5 meters. The 3 kilogram is going to move to the right 1.5 meters because it's a pulley system and they're tethered together. So this would be moving down as it hits the floor. And the final state is just the instant before it hits the floor. All right, now, that being said, since I'm considering the 2 kilogram and the 3 kilogram in my system, initially nothing is moving, so we do not have kinetic energy. The 2 kilogram object, which I'll represent with blue bars, has initial potential energy right here. The 3 kilogram object also has gravitational potential energy that's much higher. But as we go to the final state, that gravitational potential energy for the 3 kilogram one does not change. So, in essence, we have the same amount of gravitational potential energy on both sides of the equation, which means it's not going to cause any sort of changes in kinetic energy to the system. And we essentially can ignore it in our calculations because this gravitational potential energy will then go to zero towards the end. Now, as this process occurs, both objects will gain kinetic energy in this. So they will each have some kinetic energy. And since they'll have the same speed, it'll be proportionally 2/3. 2 will have about 2/3 of that of 3's. And we have then work that is being done by friction. Or if you include the floor in your system, you would have a change in internal energy on the 3 kilogram object. So notice here in green, all the bars in green represent the energies essentially associated with that, and the bars in blue represent the energies associated with the 2 kilogram object. So now as we go forward here, all right, we are going to have MT, the gravitational potential energy of 2 minus the work done by the friction on 3 is equal to the kinetic energy of 2 plus the kinetic energy of 3. So mathematically, I am going to have m2g times the height minus friction, so mu times the normal force, but the normal force on 3, times the distance it traveled, is equal to 1/2 times 2v squared plus 1/2 times 3v squared. All right, so I can rewrite this as 1/2 5v squared. And we know that 2 times 10 times 1.5 is going to be 30 minus the coefficient of friction, which is 0.5. The normal force is on a horizontal surface, so the normal force will be that of mg on 3, so this would be 30, and then multiplied by the distance, 1.5 meters. Now, we'll end up getting 30 minus 6.75 joules is equal to 1/2 times 5v squared. In solving for the final speed, we get 3.05 meters per second. Now, the one thing I am going to stress here, and I see this occur all the time, is when you guys are working with friction, and particular work done by friction, A lot of times we forget the 1.5. Okay, so just be aware when you're calculating the work done, if the force exerted is constant, you have to include that distance. You can't just have 4.5 30 times 1.5, which is 4.5. That's just a force. You have to include that distance. So you have to multiply that by 1.5. But if you include both objects in your system, this becomes a much more manageable problem. You don't have to solve for the work done by the tension in the string on 2. You don't have to find the acceleration, and you don't have to use motion equations. So understanding how to go in and out of your system and choosing the appropriate objects will make the problem much, much, much easier.